getting zapped over there. All right, so what does this look like order of complexity wise? We have this algorithm where if our strings end with the same letter, we have to recurse on two substrings of length one less than the original. Otherwise, we have to solve our problem for the first substring decremented by 1 and then the second substring decremented by 1. So suppose we want to solve this on a pair of strings of length 10 each, right? We might need to call recursively the same problem for strings of length 10 and 9, and then for strings of length 9 and 10. And the 10, 9 one we might need to solve for 10, 8, and for 9, 9. And this one for 8, 10, and 9, 9. And this one we would have to solve for 10, 7, and 9, 8. And this one for 9, 8, and 8, 9. And you can see where this is going, right? It's not a pretty picture. It's exponential, it's doubling at each branch, right? And some of these will only come down 1 if the last letter is the same, but worst case, we're growing by 2 to the n in terms of after n steps, we've done 2 to the n calls to this function. And how many of these functions do we have to do? Well, there's potentially 10 plus 10 levels to this tree, right? But it's looking like, you know, an order 2 to the n at least again. But the thing to note is that some of these functions are being calculated more than once, right? If we find the longest common subsequence of our two substrings of length 9 over here, we don't really need to call that again over here. If we do, it's going to be a whole bunch of subcalls that's going to take until the end of time. But if we pay that price over here and we can remember what the value was that we computed, we can do what's called pruning that part of the tree. We can cut that out completely, right? And this is what happens with Fibonacci numbers. When you try to compute the 10th Fibonacci number, you need to compute the 9th and 8th. And to compute the 9th, you need the 8th and 7th. And to compute the 8th, you need the 7th and 6th. And the 7th is the 6th and the 5th. And the 8th is the 7th and the 6th. And so on. But there's all this repeated structure. F of 5 is computed here and here and here and here. And here and here. And if we recompute it each time, computing the 10th Fibonacci number takes roughly 1,000 operations, right? Because this tree will have a height of 10, maybe 8 for our base cases. And it's growing, it's doubling in size at each level. But the first time we calculate f of 5, which will be right here, if we simply remember that value, then we don't need to do any of this. And all these branches that came underneath it get pruned. And this turns out to look like this. Right? The first time that we calculate f of 2, we're going to save it. And we're going to use that to find f of 3. And we'll use that and f of 2 to find f of 4, and so on. And we're going to go from 2 to the n calls down to just n. So that's another aspect of dynamic programming. Repeated subproblems, right? Cases where we're breaking our problem into subproblems, but we find ourselves solving the same subproblems again and again and again. And if we're doing that, we can increase our efficiency by caching the results of those subproblems. Store them in memory and look them up later. So have we coded this already?
It was familiar from
215, right. Okay, let's play with this. So let's write a function to find the nth Fibonacci number. So if n is equal to 0, we'll just return 1. If n is equal to 1, we'll also return 1. Otherwise, we'll return fib of n minus 1 plus fib of n minus 2. That's a straightforward implementation of this. Right, that's our recursive definition of Fibonacci's. So let's write some code. Come on. All right, so our main program is just going to take a number n, it's going to call our fib function, and then it's going to print out what the nth Fibonacci number is. And let's just do this in a loop. Will be reasonable. All right, so we'll print out the first few Fibonacci numbers. So here's our fib function. So fib 0 and fib 1 will just return a 1. Otherwise, we'll just add the two previous Fibonacci numbers together and return that. So really easy to code. I don't know what's slamming my laptop. And the first few numbers all look good. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. Those are all good. But it's slowing down. So there's 41. And we're trying to get up to 45. And it's going to take a long time, probably longer than we have. Actually, it might make 45 in a few minutes. And I stopped at 45 because 46 is bigger than 32 bits, so then you get weird negative numbers. But it's slowing down significantly. So what's going on in here? Let's put a print message in here. Let's say what Fibonacci number we're trying to find. So each time we call fib, we'll print out a message saying we're finding fib of whatever our argument n was. And you can guess what's going to happen. Right, so all that time when it was sitting there between prints, this is what it's doing. So it's mostly finding, fib of 4, fib of 3, fib of 2, fib of 1, fib of 0, 1, 2, 1, 0, 5. There's a 6. There's a 7, an 8, and a 9. But it's probably trying to find fib of 41 or 42 right now. And it's mostly spending its time refinding the Fibonacci value of these small numbers, right? This is because we're down at the bottom of that tree. And when you get down to those bottom 10 layers of the tree, right, they're all Fibonaccis of like 8 and 9 or smaller. But there's a whole lot of them, right? If we're finding fib 43, when we get down to that lower level, there's like 2 to the 33rd nodes down there. That's a lot, right? That's billions. So we're calling all of these functions, and that's what's taking all of our time. So let's put an evil global in here. So let's initialize our global count to be 0. And each time that we call our Fibonacci number function, we'll increment our global count. And when we come up here and we print out the nth Fibonacci number, let's see how many calls it took. Okay, so we got a global variable. We'll zero it out before we call fib. Inside fib, each time we go into our fib function, we'll increment that counter. And when we come back to our main program, we'll print out what the nth Fibonacci number is, and we'll say how many calls it took to compute that. Well, that doesn't look right, does it? That's okay. Yeah, I wanted to reset it to 0 before I called fib. Well, that's weird. I was not expecting that. Oh, yeah, right. Yeah, so this is a gotcha, right? If it is putting together a call to printf, right, we're kind of assuming that fib_n is going to get called before a global count is passed to printf. But it looks like it's noting the value of global count and then calculating the value of fib_n and the value of n and then passing those to printf. And so the value of global count was 0. So yeah, let's calculate fib separately and then just print out the answer here. So that's better. So the number of calls for our base cases are 1, 3, 5, 9, 15, 25, but they're growing pretty quickly. So we're doing 500 million calls now to Fibonacci. And that's what's killing our performance. So how can we fix this? Let's get rid of the global count. Money. Sorry, my Eugene Crab kicked in. All right, so let's do some saving of our values here. So I'll do another. So let's make an array called save. We're going to initialize it to 0. And save is where we're going to store the value of the nth Fibonacci number. We'll store it in save bracket n. So here's what we're going to do. We'll keep our base cases here. And we'll say, have we computed fib of n before? So if save bracket n is not 0, we'll just return the value from our save array. Otherwise, we'll do the following. So we'll calculate our return value. So fib n minus 1 plus fib n minus 2, and we'll return that as our function value. But before we return it, we'll save it. So we'll set save bracket n equal to that return value, and then we'll go ahead and return it. So exactly the same code as before, except inside here, before we recurse, we'll say, have we already calculated this nth value? If we have, we'll return it. If not, we go ahead and we do the expensive recursion, but before we return, we save that calculated value in our array. Okay, it's one write and one read. But it runs quickly. So this is like dynamic programming. Right, and the idea is we have all these common subcases. Right, and we're saving those common subcases in memory. So breaking your problem into smaller subproblems, particularly where those subproblems are calculated repeatedly, that's a good setup for dynamic programming. All right, let's look at rod cutting. So what's going on in this problem? You're tired of computer science, right? Too much work, you need a break. So you go into the metal selling business. You spend your days getting rods of metal and cutting them up into different lengths and selling those. Okay, it's a much easier business model than what we have to do in CS. So you get a piece of metal, and you're just going to chop it into a few pieces and sell those. That's how you make a living. And you didn't want to spend a whole lot of money up front, so you got a really cheap rod cutting machine that only cuts an exact number of inches. So 1 inch, 2 inches, 3 inches, 4 inches, and so on. You can't cut like a 1.5 inch length of metal. So you can only cut in these integral amounts. And it turns out that different lengths of metal are worth different amounts of money for various reasons. For example, a very long piece of metal might be valuable because somebody might want to take it and cut it up themselves. But a bunch of 3-inch pieces of metal might also be very valuable because that's the exact length that you use to build a cell phone. Imagine they have 3-inch pieces of metal inside, right? Whereas a 2-inch piece of metal is too short and a 4-inch piece of metal is too long. So it turns out if you can cut 3-inch pieces of metal, you can sell them for like $100 each, right, to Samsung. So we have a schedule which tells us a length and a price. And your length can be, let's say we're just working with an 8-inch piece of metal. So you can cut this into pieces of any length from 1 through 8 inches. And let's say the price you get for these is $1, $5, 8, 9, 10, 17, 17, and 20. So you're given this price table. You're told this is how much I'll pay for each of these different lengths. And you have a rod of material that's 8 inches long. And the question is, how should you cut this rod so that you can sell it for the most money possible? Should you cut it into a bunch of 1-inch pieces? Should you just leave it uncut and just sell it as an 8-inch piece for 20 bucks? What's the optimal way to cut this rod up to maximize the amount of money you get for it? And you know, one extreme 8-inch piece is worth 20 bucks. 8 1-inch pieces, they're worth $1 each. That's going to get you $8. That's not as good as $20. And a 7-inch piece and a 1-inch piece will get you $18. A 6-inch piece and a 2-inch piece will get you $22. A 6 and a 1 and a 1 will get you $19, and so on. So how can we find the optimal way to chop up this rod? And we can certainly brute force it, right? We could take every possible combination of cuts. We know that we could have up to 8 of these, up to 4 of these, up to 2 of these, up to 2 of these, and so on. And we can come up with some nested loops inside nested loops and just iterate over all the possibilities and add up the sums, and that will tell us all the possible values we can get, and we just remember what the maximum is. But that's really inefficient. Yeah?
Could you see that some of the lengths are made up of other lengths? Compare the composite value with the just base value?
Definitely. For example, a 5-inch length gets us the same value as a 4-inch plus a 1-inch. So if we get down to a 5-inch piece, it doesn't really matter if we cut that into a 1 and a 4 or not. But actually, if we cut it into a 2 and a 3, we'll get 13 out of that. Right? So we can do some analysis based on what that pricing table looks like, and that can lead us to some insights. But that's still a little tricky to put into an algorithm, something rigorous. This is one of these things where we're good at doing certain kinds of computations, right? We can see insights into here, but writing an algorithm for it might be tricky. So let's look at a dynamic programming solution for this. So let's just think about the first cut you're going to make on this. The first cut you make is going to give you a piece of length 1, 2, 3, 4, 5, 6, 7, or 8 if you choose to just pretend you're cutting it. Right? Don't actually cut it. Put it in the machine, but don't let any of it go under the blade and cut off 0 inches, and so you're left with a piece that's 8 inches long. But these other cuts we're going to cut somewhere, so if we cut right in the beginning, we got a piece of length 1 and 7, or 2 and 6, or 3 and 5, and so on. But everybody agrees that there's going to be a first cut we make on this, even if the first cut is, you know, at the end, so we don't actually cut any material off. We can certainly talk about the first cut. All right, so if our length is L, let's call our price P of L. That's the value for a length L piece. All right, so we have some possibilities. So here's the first cut we might make. Suppose we make our first cut to give us a 1-inch piece. Value of that piece is going to be P of 1, which according to our pricing table is 1. And we have a remaining length is 8 minus 1, which is 7. So if we cut off a 1-inch piece as our first cut, we can sell that for $1, P of 1, and we have 7 inches of material left. On the other hand, if our first cut is 2 inches, the value of that piece is P of 2, which is 5, and we're left with 8 minus 2 equals 6 inches. If our first cut is 3 inches, that's worth P of 3, which is 8, and the remaining length is 8 minus 3 equals 5 inches. In general, if our first cut has a length of I, the value of that piece is the price of I, and the remaining length is 8 minus that length I. Our first cut is going to be something between 1 inches and 8 inches, or 0 and 7 if you like. And so if we calculate the maximum value we can get from a 7-inch piece, and we add 1 to it, that's the maximum value we can get from an 8-inch piece if our first cut is 1 inch. If our first cut is 2 inches, the maximum we can get is $5 plus whatever the maximum is we can get from cutting up a 6-inch piece of rod. If we cut a 3-inch piece, our maximum value is 8 plus the maximum of a 5-inch rod. So we can write a function, max val of n. This is the maximum value from a rod of length n. And we can say for I equals 1 to n, so this value equals the price of a rod of length I plus the maximum value we can get by cutting up a rod of length 8 minus I. But it's not always 8, right? It's whatever the length of our original rod is. So let's do n minus I. And let's find our best solution. Well, our best solution, let's start off at 0. We find the value from cutting a rod of length I if that value is bigger than best, then set best equal to that value. So iterate over all the possible cuts and return our best value. So this is saying for each possible initial cut, the value we can get from that cut is whatever the price of that piece of material is worth, plus the maximum value we can get from cutting up the rest of the rod. Right? Our rod gets I inches shorter, so we're left with a rod of length n minus I, and we want the maximum value we can get from that. We're just going to call our max val function. Right? Good old recursion. So iterate over the n possible cuts, record your maximum value from each of these calculations. That's the maximum value for a rod of length n. We've still got a seg fault possibility. If n is less than or equal to 0, there's no value we can get from the rod, just return a 0. Otherwise, each time we call max val, we're getting a smaller and smaller number. If we don't end that with a base case, we'll just recurse forever until we blow up the stack. Does this make some sense? It's a different way of thinking about problem solving. But the trick is sort of grokking this, right? So breaking your problem into a set of possibilities, and for each possibility, coming up with an expression for our answer, right? So in this case, the maximum value is 1 plus max val 7. In this case, it's 5 plus max val 6, 8 plus max val 5, and so on. And this is all trying to solve max val h. But in the general case, rod of length n, right, make your first possible cut, get the value of that piece, add the max value from the remaining material. That's how much you can get with that initial cut. Find the largest value of all of those cases. That's your maximum value. So what does this look like if we try to actually do this? Right, we want to find max val of h. Well, we need to find max val of 1, max val of 2, all the way up to max val of 7. I might have something bad in here. Yeah, let me do this differently. So we're trying to find max val of h. So our first iteration, let me just do this. Our first iteration is going to say, let's cut a rod of length 1. So we're going to find the price of 1 plus max val of 7. This will be the price of 2 plus max val of 6, and so on, ending with price of h plus max val of 0. And to find max val of 7, that's the price of 1 plus max val of 6, price of 2 inches plus max val of 5, and so on. And max val of 6 is price of 1 plus max val of 5, and so on. And you can see again we've got these repeated subcases. Here's max val 5, here's max val 5. And that's certainly going to pop up in all these cases. It's going to pop up when we do max val of 6. Right, so a great setup for dynamic programming with an array to cache our results. But let's see what our max val is. So max val of 8 equals the largest of the following. So it's 1 plus max val 7, 5 plus max val of 6, 8 plus max val of 5, 9 plus max val of 4, 10 plus max val of 3, 17 plus max val of 2, 17 plus max val of 1, or 20 plus max val of 0. Well, we certainly need to find max val of 7 in order to answer this. So max val of 7 equals the largest of 1 plus MV6, 5 plus MV5, 8 plus MV4. You got the idea? And it's not as bad. We only got to find 7 values there. And we can keep doing this. And eventually we'll come down to where we're trying to find the max val of something of length 0, and that's just 0. And then our recursion starts bubbling back up. But there's an easier way to do this, which is to start at the bottom and work our way up. So imagine that we've written all of these out without actually writing them out. And let's just find max val of 1. So what's the maximum value we can get if we have a rod of length 1? It's just 1. We have no choice. We can't even cut it. We just have to sell that 1-inch piece, and we get $1 for it. Okay, max val of 2 is the largest of the following: a 1-inch piece plus max val of 1, or a 2-inch piece plus max val of 0. Well, we know max val of 1 now, right? So it's 1 plus 1, or 5 plus 0, because max val of 0 is always 0. So the largest of 2 or 5, that's just 5. So the most we can get from a 2-inch piece is $5, and we get that by not cutting it at all. So max val of 3 equals the largest of the following: price of a 1-inch rod plus the maximum value from 2 inches, price of a 2-inch rod plus the maximum value of 1 inch, or the price of a 3-inch rod plus the maximum value of 0 inches. Well, we already found max val of 2 is 5. We already found max val of 1 is 1. Max val of 0 is 0. So this is the largest of 6, 6, or 8. That's 8. And we can keep doing this. And it takes almost no time at all. If we do it like this, if we start with max val of 8 and we write it like this and we start working our way down, we've got all these repeated evaluations of different max vals. What we're doing here is we're basically caching our results by starting at the bottom and working up, right? And we're going to have to go through 8 steps before we find what the max val of 8 is. So this is sometimes called tail recursion. And it's still recursive, but it doesn't even have to be. We could just do this with a simple while loop. Because at the bottom of each loop, we've calculated the max val of the next longer piece. And when we go through the next loop, that's what we need. We need max val of 4 plus 3 and 2 and 1 and 0, which we've already computed. So it doesn't even have to be recursive. So tail recursion is where you're doing recursion, but your recursive call is the very last thing you do in your function. Right? And in that case, you can unwind it into just an iterative loop. So if you do all of this, your maximum value is going to be 2 inches and 6 inches. That's a $5 cut and a $17 cut. That's $22. That's your maximum value. Now, if we change our pricing table and make a 1-inch piece worth $3, the solution totally changes. Your best bet's going to be 8 1-inch pieces. That's going to get you $24. So very hard from looking at the table or looking at solutions to a particular table to understand how the solution changes when you change the pricing schedule, for example. Right? There's not a good intuition for how that relates, which is why we have algorithms. All right, so questions on this. This is a lot of stuff, okay? When I was an undergrad, this was an entire course, theory of algorithms. We looked at different kinds of algorithms. We worked on proving the correctness of algorithms, right? How do you rigorously show that this is going to give you the maximum value, or that a bubble sort's going to sort your numbers? We looked at proving the time complexity of different algorithms. Right, there's a lot of depth you can go into on this. This is a sort of high-level overview of some different styles of algorithms. But it's a lot of material, right? It's a lot of concepts. So it's going to take a while to sink in. But with what we've done so far, anything I can clarify or any questions? So let's look at a different problem and a different style of algorithm. So I don't know if this is the official name or not, but it's what I'm going to call it, the fractional knapsack problem. So here's the idea. You ever see one of these things where somebody's like the 1 millionth customer in a store and they win like a shopping spree or something? So imagine that, you go through a store, you're the 1 millionth customer, and they say, you've won a shopping spree here. This is the deal. We're going to give you a bag, and anything you put in this bag, you get to keep. Right, take as long as you want, figure out what you want to put in the bag. Anything that you can put into this bag that fits in the bag, you get to keep. Right? So depending on what kind of store it is, you might put different things in this bag. If you're at a bank, you just grab the $1 million bills, right? Fill your bag with it and walk out. Okay, suppose you're in a food co-op, right? So it's all like locally grown stuff, and it's one of these places where everything comes out of a big bucket, right? So there's all these buckets with lids on top and scoops, and you can scoop stuff out of there, scoop some oatmeal, scoop some sunflower seeds and some pistachios, right? And this is how you buy your food, so like bulk food place. And suppose you have a pricing table. So here's your item. Here's price per pound. So oats cost $1 per pound. Pumpkin seeds cost $3 a pound. Pistachios cost $10 a pound. Any cooks in here? How much does saffron cost? How much? Yeah, it's really, really spendy because it's really light. Let's say $1,000 a pound. Is it really $12 an ounce? Yeah. I don't think you can get an ounce for 12 because it weighs nothing. So saffron, $1,000 a pound, right? This stuff is priceless. It comes from, I think, the pistil of a certain flower. Yeah, and it's hand-picked, and it takes a lot to get a pound of this, right? But it's a really good spice. All right, so you have a bag. It will hold let's say your bag holds 10 pounds. Okay, so it's done by weight instead of volume. If there's an unlimited amount of all of these materials, all of these items in the store, what would you put in your 10-pound capacity bag? 10 pounds of saffron, right? $10,000 right there. It would make no sense to get 5 pounds of saffron and 5 pounds of oats, right? Because that's worth $5,005, right? Unless you really like oatmeal. You can sell your saffron though, right? So you're going to load up on this, right? But suppose there's shortages. Suppose there's only a certain amount of each of these things available. Suppose that there's only 1 pound of saffron available, and there's 5 pounds of pistachios, and there's 10 pounds of pumpkin seeds, and there's 100 pounds of oats. Now what would you put in your bag to get the maximum value? Saffron, how much? 1 pound. You got 9 pounds left. What are you going to do with that? Take the pistachios, how much? All of it, 5 pounds pistachios. Are you done? What else goes in your bag? 4 pounds of pumpkin seeds. You still don't get any oatmeal. All right, how did we come up with this solution to the problem? What was the algorithm you just used? Mm-hmm. Take as much as you can of the most valuable item, right, until your bag is full or there's no more of that item left. If there's no more of that item left, move on to the next most valuable item. And either fill your bag or exhaust that item and then move on to your next most valuable item. Okay? The name for this kind of algorithm, appropriately enough, is a greedy algorithm. It's greedy in the sense that it tries to solve your problem right now. Okay, you're trying to do whatever you can right now to get the best possible solution. So greedy algorithms, typically they start off and the steps that they're making at each step are moving you towards an optimal solution based on what gives you the best partial solution. Okay, it's not doing any look ahead. And with the rod cutting problem, we can't do this. Right? Rod cutting will not yield to a greedy algorithm. Well, I don't even know what greedy would be here, but greedy might be like, well, let's get $20, right, for our first piece. Or maybe we could price it out to like value per inch and start off by cutting off the most valuable pieces. But as we'll see Wednesday, that's not going to work for this or for a different kind of knapsack problem where we're working with whole numbers of items. Okay, if it's fractional, if you're allowed to take pieces of this, greedy algorithm always gets you the optimal solution. But we're going to talk about what's called a 0-1 knapsack problem, where you have to take an integral number of items. So our items are things like cell phones and pencils and laptops, right? And you can't take half a laptop. And we'll see some examples where a greedy algorithm does not get you the optimal solution. Okay, and then we'll look at a dynamic programming approach similar to the rod cutting problem that will get us an optimal solution. And then we'll talk about PA5, and I haven't decided if it's going to be subsequences or knapsack. I got to code up a sequence one and see how that looks. Yeah, just grab the battery, right? Oh yeah, right.